Now we are talking about performance factors and system attributes. Sometimes you must answer the questions like, what components of the computers make to make it fast? The CPU, the RAMs, or the HDD? For end user, the answer is simple, all of them. But as an engineer, your answer must be more professional-like. The rationale must be based on performance factors that we can withdraw from the previous formula, calculating the CPU time. Let's take a look at this formula that you already know from the previous sections. CPU execution time equal to the total instructions of the programs times the CPI times the clock cycle time. Or if you write it in more details, this formula can be written like this, in which the CPI is expressed in terms of P, M, and K, where P is the numbers of processor cycles need to decode and execute the instructions. M is the numbers of memory reference need. You know, when the CPU wants to read something from the memory, it will need to take some clock cycle to access the informations, right? And K is the ratio between the memory cycle times and the processor cycle time. The reason of K is that, you know, the CPU is much faster than the memories. For sometimes with one clock cycle in the CPU, it will take maybe 3 or 4 clock cycles in the main memory. So the K is the ratios between these values. Okay, so it is easy to realize that the time taken to complete a program depends on IC, P, M, K, and tau, which are performance factors. To make a program fast, those factors must be contributed accordingly to the speed of the systems. And now we want to take a look at the relations between the performance factors and the system attributes of the processor. There are 4 system attributes that we want to take into consideration here. That is the instruction set architectures, the compiler technologies, the processor implementations, the cache and memory hierarchy. And in the columns we have the performance factors, instruction count, the time that the CPU needs to decode and execute the instructions, the numbers of memory that the CPU needs to refer to when it executes an instructions, and K is the ratio between the times, the CPU times and the memory times, and tau is the clock cycle times. So in this table you can see that the numbers of instructions will depend on the instruction set architectures here, and the numbers of instructions will depend on the compiler technologies. I will give you the rationals. I want to bring the table to this board, and now I will explain it on this board. Now I will give an example so that you can understand why we have this and why we have this. The number of instructions or instruction count. Let's take a look at a simple programs. X equal to X plus Y. This is an assignment instructions in C language in which X will be accumulated by Y. The current value of X will be added to Y, and the result will fall back to X. If this instructions is compiled into machine code, you can have instruction like this: load X, add Y. This is the instructions from the ARM architectures. Load X, that means X will be loaded into AC. AC, that means accumulators. And add Y, that means AC will store the values of current AC add with Y. So now in the end, in AC, it will carry the values of X plus Y. Now in assembly language that you write in Intel x86, move AX. These instructions will be translated like this. AX equal to X. This will be translated to AX. Now carry the values of the current AX, add up with Y. So essentially, those instructions are the same, but they rise in a different ways because the previous one is written in ARM architectures and the next one is written in x86 architectures. But there are CPUs that you can, if you want to add these instructions, you can try like this, add AX, X, Y. That means AX equal to X plus Y. This is another architectures. This example clearly explains with different instruction set architectures, we have different machine code. And this architectures, we have IC equal to. This one we have IC equal to. And with this one we have IC equal to 1. That means the instruction set architectures affect the numbers of instructions in the programs. Okay, about the compiler technologies. You can refer to the data flow analysis, the engineering that has been applied to the designs of the CPU. That sometimes the compiler, if they can look at the meanings, if they can understand the meanings of the programs, it can deduct the result, and sometimes with the long programs, it can compile only a single instructions. For example, in our last example, as you remember, we have these programs A equal to 1, B equal to 2, and C equal to 3 if X equal to A plus 5, right? Else X equal to B plus 4. And lastly, we have C equal to X plus 1. As we already explained recently, this always equal to 6, this always equal to 6. That means C always equal to 7. With the data flow analysis, the compiler to translate these instructions only into the machine code here, right? And it's apparently that the number of instructions here will be reduced drastically.